Welcome to Lecture 8.2, Part A. 8.2 is titled Graphs of Other Trig Functions. So just to remind you, in 8.1, we learned all about the sine and the cosine functions. And in Part A of 8.2, we're going to go over the tangent function, and we'll do a couple of examples using the tangent function. And then we're going to look at the basic forms of secant and cosecant. In Part B, we'll come back and we'll do examples of graphing transform secant and cosecant, and we'll cover cotangent in Part B as well. So once again, in this particular Part A lecture, we're going to cover the basics of tangent, and we'll do some examples of graphing transform tangent functions, and we will just cover the basics for secant and cosecant. Okay, so I just included the unit circle so that we can refer to it as needed. Okay, so let's start out with analyzing the graph of tangent. Now, we know from our previous studies in Chapter 7 that tangent is equal to the sine over the cosine. What I did here was I created an x f of x table with some common x values used in Trig here that move around our unit circle for us. And I went ahead and input the sine and the cosine values, because then all we have to do is come back and divide these values to see what the tangent at that same x value is. So for example, the tangent of x here when x is 0, well, that's just the sine of 0, which is 0, over the cosine of 0, which is 1. So the tangent of 0 is just 0 there. Okay, so that's what I'm going to be doing to fill in the remaining boxes to the right. And then I put an extra set down to give the decimal equivalent to all these values so that you can kind of get a sense numerically of where these numbers sit. Okay, so I'll do some side work for some of these. So this next one, when we take the tangent of pi over 6, that's just the sine of pi over 6, which is 1/2, divided by the cosine of pi over 6, which is square root of 3 over 2. So I get 1/2 times the reciprocal, 2 over the square root of 3, and that's 2 over 2 square root 3. My 2's divide out, and I get 1 over the square root of 3. I can't leave that with the root in the denominator, so I need to rationalize it by multiplying by the square root of 3 over the square root of 3. And finally, I get square root 3 over 3. So this is square root 3 over 3. Now, I've already completed all of this background math type things here for the whole chart. So I'm not going to walk you through doing the division of sine over cosine for every one of these. I think this is the tangent of pi over 6 is a good enough example that you know how to move through the rest of this chart. So let's look at the tangent of pi over 4. That's square root of 2 over 2 divided by square root of 2 over 2. Anything divided by itself is 1. And then I end up getting the square root of 3 here. Oops, that's a 3. Let me rewrite that. Square root of 3. There we go. Now, notice, with the tangent of pi over 2, I have 1 divided by 0. That is undefined. because division by 0 is undeterminate. We have vertical asymptotes that show up when these functions are undefined. And I'll show you a little bit more about that here in just a moment. Okay, for the tangent of 2 pi over 3, I get negative square root 3. For 3 pi over 4, I get negative 1. 5 pi over 6, negative square root 3 over 3. And for pi, I get 0. Okay, so I'm going to go ahead and draw on the graph that we have a vertical asymptote where the function is undefined at pi over 2. And so, because that I suspect I may have more things like this going on in my function, I'm going to choose other increments of pi over 2 that I suspect may be undefined. Now, I know 2 pi over 2, which is pi, is 0. So I could go ahead and put pi 0 on my graph here. And I can also put, let's see, 0, 0. So it looks like every increment of pi, I'm getting a 0 output value. So let me check the tangent of negative pi over 2 and see what happens. So that's the same thing as the sine of negative pi over 2 over the cosine of negative pi over 2. Now let's flip back to our unit circle. Okay, so when I have negative pi over 2, that actually takes me to 3 pi over 2. I have negative 1 as my sine and 0 as my cosine. So what I have happening here is negative 1 over 0, which is also undefined here. So sure enough, I have another vertical asymptote sitting at negative pi over 2. So I'm going to have another vertical asymptote at negative 3 pi over 2 and positive 3 pi over 2. Which also means I suspect that I will have 0 at negative pi. Let's check it. Tangent of negative pi is the same thing as the sine of negative pi divided by the cosine of negative pi. Okay, let's go back to our unit circle. Negative pi is the same thing as pi. And so I get the same value as I get when I get pi. So that's just 0. So sure enough, every pi increment in either direction starting at the origin is a point on the graph. And every pi increment starting at either negative pi over 2 or positive pi over 2 is going to be an asymptote. Okay, now let's fill in a few more points and see if we can get an idea of what this graph actually looks like. Okay, so I have some nice, neat points that I can go ahead and fill in. I know that pi over 4 gives me an output of 1. Okay, so halfway between 0 and pi over 2 is pi over 4. So that little tick mark halfway between 0 and pi over 2 represents pi over 4. So I can go ahead and go up 1 on that. And I can have, let's check negative pi over 4, so I can work between my two asymptotes here. So the tangent of negative pi over 4 is equal to the sine of negative pi over 4 over the cosine of negative pi over 4. Let's go back. Okay, so the sine and the cosine of negative pi over 4 takes us to 7 pi over 4. So I have negative square root 2 over 2 divided by square root 2 over 2, which just gives us negative 1. So this is negative 1 right here. So at negative pi over 4, I have negative 1. Okay. So let's do a couple more points in there, and then we'll move forward to the shape of this thing. All right. So let's choose, how about negative pi over 3. So the tangent of negative pi over 3 is equal to the sine of negative pi over 3 over the cosine of negative pi over 3. Okay, let's go back to our unit circle. Let me get a different color here. Negative pi over 3 takes me to 5 pi over 3. So I end up having negative square root of 3 over 2 divided by 1/2. Well, if I look at my column for pi over 3, I have the same division happening here, except the only difference is when I'm at negative pi over 3, that square root of 3 over 2 is negative. So I'm going to get negative square root 3 there. And when I put the negative square root of 3, well, when I put the square root of 3 into my calculator, I get 1.73. So this is going to be negative 1.73. Okay, so negative pi over 3 lives somewhere around in here, and that is going to be negative 1.73, so maybe about right here. Now let's take positive pi over 3, which we already have. The calculation for that lives about right here, and it is 1.73, which is about right here. Okay, so it looks like this is just about forming a line, but it's not, because remember, you can't cross over those vertical asymptotes. So what this looks like is it follows the asymptote, it does an S-curve across the x-axis, and then it goes off into positive infinity. And okay, so let's look at a couple more points so that you can see what's going to happen between, the same thing's going to happen between all of your asymptotes here. So let's look at 3 pi over 4, and that is negative 1. This is 3 pi over 4 right here, and we get negative 1, which means that, let's see, 3 pi over 4, 3 pi over 8 is right here. It's going to give us positive 1, so this thing's also going to go like that. And so this one comes up, and we continue off. So I'm just going to put my two little markers there that are one away and one down and one above from it. Same thing here. I'm coming up from here. All right. So that is what the tangent of x looks like. Let me also point out that the tangent is an odd function. So that means when you plug in negative x into that function, you're going to get out the negative tangent value of positive x. And we can see that exemplified right here. When I plugged in negative pi over 4, I got negative 1, and when I plugged in positive pi over 4, I got positive 1. And it also has origin symmetry. You can see that it has origin symmetry. All right. Now starting to work with transforming these tangent functions. Okay, so we're given the instructions. If you're given a tangent function in the form of a times tangent of bx, so we're just talking about multiplying by a stretch factor in my vertical direction and in my horizontal direction. So that gives, the horizontal direction gives me the period, and the vertical direction is my a. That's a stretch or compress in the vertical direction. So if that's all that we have going on in the tangent function, this is how we graph one period of that particular function. Okay, so our first task is to figure out the stretch factor. And the stretch factor is given by the absolute value of a. In this case, that's the absolute value of 3, which is 3. Okay, so you can see that that a value right there is 3. All right, our next task is to identify b and determine the period for the function. So my b value is pi over 6. And my period is equal to pi. Remember, we're moving in increments of pi because from negative pi over 2 to positive pi over 2, I've got a pi distance between there. So it's pi divided by the absolute value of b. And in this case, that's pi divided by the absolute value of pi over 6, which is the same thing as pi over 1 times the reciprocal, 6 over pi. So I'm getting a period of 6. Now, I have not shifted up or down or left or right. So I know my point, my first point that I want to identify is the same one that we first identified on the parent form of the tangent function, and that is the origin. I know I've got that point there because I have not moved left or right or up and down. I don't have a C or a D value that's different than 0. It's not even showing up here because they're both 0. So if the origin is in the middle of my period, look here, the origin sits right at the midpoint between my period boundaries here, then I know since my period is 6, I need to move 3 in the negative direction for my period boundary and 3 in the positive direction. So all I did was half 6 and moved that distance in each direction. Okay, so I've got my period boundaries here. Now it says, okay, if A is greater than 0, then my graph approaches the left asymptote moving in the negative direction, and it approaches the right asymptote moving in the positive direction. Okay, so I know from that statement there that I am, at the very least, dealing with this and this. Now I just need to find a couple points between that I know are on the function so I can get a more accurate picture of my curve there. And that's where we plot reference points. Now we've already got the 0, 0 there because we did not shift. So I need to find 2 points. One point is P divided by 4A. Okay, so in this case, that is 6 divided by 4, 3, which is the same thing as 3/2, or 1 1/2, 3. All right, so 1 1/2 is right here. Let's see, 1 1/2 is right here. And I move up 3. 1, 2, 3. Let me make those a different color. Okay, and then my other reference point is given by negative P over 4, negative A. So that's going to be negative 3/2, negative 3. Let me go ahead and put my point there. Negative 3/2 is negative 1 1/2, negative 3, 1, 2, 3, right here. And now I'm ready to connect to get the general shape of that tangent function. Okay. All right, so things to note about the tangent function in its expanded standard form here. So y equals a times the tangent of b times x minus c plus b. The stretch factor is the absolute value of a. The period is pi over the absolute value of b, and these are all bigger on your note sheet. So if you don't have the note sheets printed out, you need to have those when you watch these lectures, because sometimes I have to shrink things to fit them on the slides here. But it's much clearer and a little bigger on your actual note sheet. The domain is x not equal to c over b plus pi over the absolute value of b times k, where k is an integer. In other words, since the domain is where, let me rewrite this so that I can explain what this is saying. It says the domain is when x is not c over b plus pi over the absolute value of b times k. The reason the domain is not there is because that is where you're going to have vertical asymptotes. And actually, I take that back. It's 2b, 2 times the absolute value of b in the denominator there. I wonder if that is, okay, no, that's where your vertical asymptotes are going to be. Okay, so the range, you have negative infinity up to negative absolute value of a, and then absolute value of a to positive infinity. Okay, so let's walk through the steps of how to graph one of these things. And we'll use this example below here. Okay, so we're given the example of y equals negative tangent of pi x plus pi minus 1. So the first thing I'm going to do is identify my a, b, c, and d values. And I'll color code them just to keep them straight with everybody. So my a is equal to negative 2. My b is pi. Now this one's a little tricky. My c is negative pi because minus is in the form inside the function, so this is minus negative pi there. And my d value is negative 1 on the outside right here. So I have had a shift. I've had a shift of negative pi, negative 1. No, I'm sorry. Not negative pi, negative 1. Let's walk through the steps. So it's actually negative 1, negative 1. Okay, so because I have to divide my c by my b to get my my shift there. All right, so let's start with the first step. Okay, we've expressed the function. We've identified a, b, c, and d. Identify the stretch factor. Okay, so the absolute value of a, my stretch factor. I'm just going to write stretch. The absolute value of a, which in this case is the absolute value of negative 2, which is 2. All right. Now we want to identify b and determine the period x over the absolute value of b. So my period equals pi divided by the absolute value of b. That is pi divided by the absolute value of pi. So that's just pi over pi, so that's 1. There we go. Now we're starting to get somewhere here. Okay, so that was this one right here. I now need to determine my phase shift. Okay, this is where I'm going to start grabbing the other coordinate for where my origin moved to, where 0, 0 actually moves to. That gives me my shift. Okay, so phase shift is given by C over B. C in this case is negative pi. B is pi. So that is negative 1. All right. So because, okay, hopefully this will make sense. I'm shifting negative 1 in my horizontal direction, and I'm shifting negative 1 in my vertical direction. Let me go back to our parent form of the tangent function. Remember, it went through the point 0, 0. So because I'm shifting negative 1, that point 0, 0 moves to negative 1, negative 1. So I'm going to go ahead and put the point -1, -1 on my graph, and that is right here. So what happened was my point 0, 0 shifted to C over B. This is C over B and D. So that's how you find that point that would generally be sitting at the origin if you had not shifted. Hopefully that made sense. I don't have anybody in the room with me this morning, so I'm having to just rely on myself to know if I've covered it well enough for you. But as usual, you can message me with questions if you have it. Okay, so draw the graph of y equals a tangent b of x shifted to the right by c over b and up by d. So I went ahead and graphed that point. Already done that. Check. Sketch the vertical asymptotes. Okay, so we have, let me get a different color. Let me get the green. We have vertical asymptotes located at x equals c over b. So there's my shift, my horizontal shift, plus pi over 2 times the absolute value of b times k. And k is some odd integer. Okay. So, I am going to use k values of -1 and 1 just to see if I can surround my point -1, -1 with asymptotes. So this is what that's going to look like. This is when k is equal to 1. I get x is equal to c over b, which I already know is -1 from over here. -1 plus pi over 2 times b, the absolute value of b. The absolute value of b is pi, so this is over 2 pi. Times, I'm going to use a k value of 1 this time because that is an odd integer. So I have -1 plus my pi's divide out. It's 1/2. And that leaves me at -1/2. So I have a vertical asymptote here at -1/2. Now I'm going to try to get on the other side of my point. So I'm going to use a k value of -1. So x equals -1 plus pi over 2 pi times -1, which is -1 minus 1/2, which is -1 and 1/2, right here. All right, so I've got my vertical asymptotes. I've got my center point. Now I just need a couple of reference points. And I'm going to use reference points that lie halfway between my main reference point and my vertical asymptotes. So I'm going to go for, I'm going to see what happens when I plug in -1.25. Let's see, -1, 1, 2, 3, 4, 5. So -1.25 is going to be about right here on the x-axis. And I'm also going to try -0.75, which is about right here, and see where those points lie. Okay, so I have if x is equal to negative 1.25 of y equals negative 2 tangent of pi times negative 1.25, and I'm just putting this into my calculator, plus pi minus 1. And when I put that into my calculator, I get out positive 1. So I have the point negative 1.25, positive 1, which is right here. And then if x is negative 0.75, I put all that into my calculator, and I get out that y is equal to negative 3. See, 1, 2, 3, about right here. Okay, so because you know the general shape of the tangent function, we know that it follows that asymptote, it crosses over, and then it follows the asymptote again. Notice this is flip-flopped from our parent function, but I will also point out we had a negative tangent function that we were dealing with, so it reflected it over the x-axis. And that's it for that one. Okay, so this next problem here, I got into this problem and was working it before I came to present the lecture to you. And I figured out that I need to contact the company, the textbook company, because you have to use a point on the function to finish off writing the equation of it, and it's really ambiguous. I actually had to look at the answer and work backwards to figure out what an exact point on this function is. So I'm going to give you another point on this function, and you'll see in a moment why we need this point, why we need to know the exact value of this point. So I'm going to let you know that this point right here on the function is the point pi over 8, 4. Like I said, please, I had to work backwards from the answer to figure out what that point was. So don't worry about how I found that. Just know I'll be contacting the textbook company to see that they identify one other point on the function so that you're not having to guess. So hopefully this example will help all of this business make sense to you. All right, so we're asked to write the equation of this function here. So we're given the graph of a tangent function, and the first thing that we need to do, which, by the way, we're trying to write something in the form of y equals a times the tangent of bx minus c plus d. So that's what we're trying to write. So first off, I will point out that we know this goes through the origin, which means that C is going to equal 0 and D is going to equal 0. So I've had no horizontal or vertical shifting happening here. So actually, I'm going to be writing an equation in the form of y equals a tangent bx. But I just wanted to point out how we knew that C and D were 0. Okay, so the first step is to find the period P from the spacing between successive vertical asymptotes. Well, I have a vertical asymptote at negative pi over 4. That's halfway between 0 and negative pi over 2. And I have one at positive pi over 4, which is halfway between 0 and positive pi over 2. So this distance between my asymptotes, which is my period, this distance is pi over 2, half of pi. And I'll show you how I got that. I'm going to take the absolute value of the distance between my asymptotes. So I have an asymptote at negative pi over 4. And the distance, so I'm going to subtract them, or the difference, I have one at pi over 4. So that is the absolute value of negative 2 pi over 4, which is the absolute value of negative pi over 2, which is just pi over 2, or half of pi is my period. Okay, now to figure out what my B value is, well, I know that my B value is equal to pi over my period. And that just comes from, if I have my period equaling to pi over the absolute value of B, if I multiply both sides by B, we'll just say it's positive. So B times B, those B's divide out, and now I have BP equals pi, and then I come back and I divide P off of both sides. I get that B equals pi over P. So we just rearranged that information about the period to get that B equals pi over P. And I know my period now, it's pi over 2, so I can plug that in and solve for B. So this is the same thing as pi divided by pi over 2, which is the same thing as pi over 1 times the reciprocal 2 over pi, which is, my pi's divide out, that's just 2. So now I have a B value of 2. And then I need to use any other point to be able to determine what my A value is. So I know that I'm trying to get to this form here. So far, this is what I know. So far, I know that y is equal to some A value times the tangent of 2x. Okay, so if I have one other point, I can solve for A because I can plug that in for x and y. This is why I said at the very beginning, they really should have given us another point that we could know for sure and not have to guess at. This graph is not very exact with, there's no grid floating around on it. So like I said, I had to go look at the answer and work backwards to even get this point to give to y'all. But I'm going to show you how when you do have another point on the function that you can solve for that A value. So I'm going to plug in the point pi over 8 and 4. So 4 and then pi over 8 is going to plug in for x there. This is equal to some A value that I'm looking for times the tangent of 2 times pi over 8. Okay. 4 equals A times the tangent. Okay, 2 times pi over 8 is 2 pi over 8. 4 equals a times the tangent. That's the same thing as pi over 4. And if we look back, we know what the tangent of pi over 4 is. The tangent of pi over 4 is 1. So this is just 4 equals a times 1. So a is 4. I'm now ready to write my equation. The equation of this tangent function is y equals 4 times the tangent of 2x. All right, we have a couple more to look at. All we're going to do from here out is just look at the basic forms of secant and cosecant. I wanted to keep this right at an hour, and this is another one of those hefty lessons to get through, so I'll record part B tomorrow for y'all. And I'll let y'all know that, of course, in a message later on this morning. Okay, so the secant. We know that the secant is the reciprocal of the cosine function. So I took that same chart that I created for the very first page that we looked at, the tangent function, and I just pulled the x information and the cosine information. Because now if I divide if I divide 1 by each of my cosine values, I'm going to get the secant. Because the secant is equal to 1 divided by the cosine of x. Oh, excuse me. Okay, so the secant of 0 is 1 divided by 1, which is just 1. And I'll work one of these out for you. The secant of pi over 6 is equal to 1 over the cosine of pi over 6. The cosine of pi over 6 is square root 3 over 2, which is the same thing as 1 times 2 over the square root of 3, which is 2 over square root 3. I've got to rationalize that denominator by multiplying by the square root of 3 over the square root of 3. And I get 2 square root 3 over 3. So this is 2 square root 3 over 3. Okay, so I've done all the other calculations here. This is 2. No, I'm sorry. This is square root of 2. There we go. This is 2. 1 divided by 0 is undefined. Negative 2, negative square root 2, negative 2 square root 3 over 3, and negative 1. Okay. So we know we're undefined at pi over 2. So I'm going to go ahead and put my vertical asymptote there. And I know I have the point 0, 1. I'm going to go ahead and put that on my graph. 0, 1. All right, so I'm going to do something a little clever before we actually move into graphing the secant function further. Since it's the reciprocal function of cosine, I'm going to graph the cosine on here. I'll do it in a light pink color. Cosine starts at 0, 1, and it coasts down through pi over 2. It hits its bottom at pi at negative 1, comes back up, and at 2 pi, it's back up to positive 1. Let's move in the other direction. Okay, so cosine looks like this. Snaking through here. Okay. So I have my asymptote. By the way, this is cosine of x. And I'm going to use it to graph the secant of x. All right, so I have my one asymptote there, and that one asymptote fell at pi over 2. So I suspect that I may have another asymptote at negative pi over 2. So I'm going to evaluate the function at negative pi over 2. Secant negative pi over 2 is 1 over the cosine of negative pi over 2. Back to our unit circle. Negative pi over 2 takes me here, and the cosine is 0. So that's 1 divided by 0, which is undefined. So sure enough, I've got another asymptote at negative pi over 2. So those are going to happen at every pi value. So I have a period of pi. So I've got a vertical asymptote here. And notice my vertical asymptotes are where the x-intercepts of cosine are, because they're reciprocal functions of each other. If the cosine has an x-intercept, that means that that y value is 0. So if I flip-flop that, that's going to put 0 in my denominator when I am taking the secant function, the reciprocal cosine function. So that's going to create vertical asymptotes all the way across where my cosine function has x-intercepts. All right, let's get a couple more points onto the graph here to try to see what's going on with this function. All right, so let's see. Pi over 4, the reason I'm choosing pi over 4 is because it's sitting there as a hatch mark on my graph, has an output value of square root of 2. The square root of 2 is approximately 1.41. So at pi over 4, I have 1.41, about right here. At, let's check negative pi over 4. See if we get some mirroring happening. So the secant of negative pi over 4 is the same thing as 1 over the cosine of negative pi over 4. The cosine, I think we have it here. Nope. The cosine of negative pi over 4 takes us here to 7 pi over 4. That is square root 2 over 2, which is the same thing that we got for positive pi over 4. So these are going to be equal. This is just going to be the square root of 2. So I'm going to have another positive value here. And I can do pi over 6. Let's see if I've got some nice, neat numbers for pi over 6. No. The 2 times the, I'm sorry, not pi over 6. Let's do, let's see, that was pi over 4. Let's do pi over 3. That's nice and neat. Pi over 3, 2. Pi over 3 lies between pi over 4 and pi over 2 about right here. So that comes out at positive 2. And sure enough, if you do the math, negative pi over 3 comes out at positive 2 as well. So I've got asymptotes, so you get this U shape. That is sort of a mirror reflection of that cosine, but it's not really, because the cosine passes across those asymptotes, because those asymptotes are not for the cosine, they're for the secant. For the sake of time, because I'm about to run out of my hour, if you plug in more points, you'll find that it always goes through the higher the low point of the cosine function, and whichever way that high or low point is moving, so if it's in the negative direction, that the corresponding segment of the secant function is going to be opening down. If my max, or if my maximum is, if I have a maximum, I'm opening up basically with my secant. If I have a minimum with my cosine, I'm opening downward with my secant. So this one's going to open downward. And this one's going to open upward. All right, that's the basic secant function. Now let's look at cosecant, and then we'll be done with this part of the lecture. All right, secant is the reciprocal sine function. So I'm going to go ahead and graph sine on here. Remember, sine starts at the origin, and it has a period of 2 pi. I'll go in both directions. So here's my sine function. And it's going to be the same type of looking curve as the secant was, the cosecant. The secant is just shifted from the cosecant because sine is shifted from cosine. So this cosecant function is the reciprocal sine function. I'm going to go ahead and fill in all the values. I've already done the work for you. So this is undefined. This is 2. This is square root 2. 2 square root 3 over 3. 1. 2 square root 3 over 3, square root 2, 2, undefined. Okay, so we actually have 2 of our asymptotes on here. I have an asymptote at 0, so right on the y-axis, and I have an asymptote at pi. So you can see a period of my cosecant function is pi. So I can go ahead and know that I've got one here, I've got one here, I've got one here. And like I said, for the sake of time, it follows the same exact pattern as the secant. So if I have a high point, and it hasn't been reflected, if I have a high point, a maximum on my sine, let me label that this is sine. The sine of x. If I have a maximum, that piece is going to be opening upward. And you can go back and fill in the points and see that it makes that same U shape. So here I have a minimum, so I'm going to be opening downward, going through that minimum point. Same thing here. All right. That is what I have for you for this particular part of the lecture. When we come back for part B, I'll be moving through examples of graphing these things or writing equations of them, and we'll also hit up the cotangent function. Thanks. I hope this was helpful.